Hi everyone, this is Dr. V.T. Gopinathan, working as an associate professor in the Department of Aeronautical Engineering of Hindustan College of Engineering and Technology, Coimbatore. In this flight dynamics video, we are going to discuss about solving the previous year gate questions from aerospace engineering code that too connected with the cruising level flight performance. The first problem is if lift coefficient at thrust required minimum is 0.85 and induced drag factor K is 0.0085, then we have to find the approximate value of drag coefficient at zero lift, that is CD naught. We have to find. The multiple options are given. We have to find the right answer. To solve this problem, we know that for steady level flight, we know the condition, whereas the forward force thrust is equated by the rearward force D. So T is equal to D. So from the given condition thrust required minimum, we can write the first one. We can take it here. The first one is thrust required minimum is equated to drag minimum. For the drag minimum, we know the condition zero lift drag coefficient is equal to drag due to lift coefficient. That is CD naught is equal to KCL square. So this is the formula we can apply here to find the solution. So this is a direct substitution. So CD naught is equal to the given K value is 0.0085 and CL square 0.85 square. So the final answer is CD naught is equal to 0.0061. So the first option is the answer for this question. We can move to the next question. From the given problem, the pitot tube of an aircraft registers a total pressure value P naught is equal to 54051 Newton per meter square. They have given the static pressure value, that is 45,565 Newton per meter square. The density value is 0.6417 kg per meter cube. Then we have to find the indicated airspeed. To solve this problem, we know the basic condition. The total pressure is equal to static pressure plus dynamic pressure. So the total pressure P naught is equal to static pressure PS plus the dynamic pressure can be written as half rho V square. So this is the direct formula again. Here the given V value is, take it as a indicated airspeed. So the rest of the values are available in the problem. Then we can substitute the value. So the P naught is 54051. Then PS is 45565, then half 0.5, rho value is given 0.6417 into V square. Here we have to find the V square value. So the final V square value is V is equal to 162.6 meter per second. So the second option is the answer for this problem. So we have to remember the basic formula. P naught is equal to PS plus half rho V square to solve this problem. So this is the simple one. Then we can move to the next problem. The next problem, an aircraft in level and unaccelerated flight, that is the condition they have given. The velocity value is 300 meter per second. Requires the power value is 9 into 10 power 6 watts. If the aircraft weight is 1.5 into 10 power 5 Newton, then we have to find the L by D ratio, that is lift to drag ratio. Again, we have to consider the cruising level flight performance here. From this figure, we can take that. That is the upward force lift is compensated by the weight, then forward force thrust is compensated by the drag. So we know the basic condition, the power is equal to force into velocity. With respect to this, the force can be thrust, then it is multiplied by the velocity. For steady level flight, thrust is equal to drag, so drag into velocity. So this is the formula we are going to use because we have to find the L by D ratio. From the given data, the power value is given, that is 9 into 10 power 6. Then we have to find what is drag value. The velocity is again given, that is 300. So drag is equal to 9 into 10 power 6 divided by 300. So the D value is 3 into 10 power 4 Newton. So to find the L by D ratio, we know what is L. Again, for the steady level flight condition, the lift is equal to weight. So L by D is equal to the weight value is given, that is 1.5 into 10 power 5 divided by 3 into 10 power 4. So the L by D ratio is 5. So the option 4 is the right for this. So we have to remember the condition for steady level flight, that is T is equal to D and L is equal to W, and we know the basic equation, power is equal to force into velocity, to solve the problem and find the answer. So the next problem is a conventional aircraft, low speed aircraft had the following aerodynamic characteristics has been given. The CD0 value is given in the problem, that is 0 lift drag coefficient, that is 0.020. Then Oswald efficiency factor is mentioned, that is E is equal to 1. The aircraft was flown to maintain a steady level flight, and for the minimum thrust required, again they have mentioned the condition minimum thrust required. The lift coefficient is 0.8. Then we have to find the numerical value of aspect ratio. Aspect ratio is the non-dimensional number here. So to solve the problem, we should know the basic formula of the aspect ratio, whereas the aspect ratio is equal to the square of the span, that is B square, divided by wing platform area, that is S. Again, for the steady level flight, we know the condition thrust is equal to drag. So here they have mentioned minimum thrust is required. So T or minimum can be equated by D minimum. Again, we can remember the first problem what we have applied already. That is CD0 is equal to KCL square. That is the condition for minimum drag. So we know the proportionality constant value K is equal to 1 by pi EAR. So this is the formula again we are going to use. So CD0 is equal to, in the place of K we can substitute pi EAR, 1 by pi EAR multiplied by CL square. So CD0 is equal to CL square divided by pi EAR. So here we have to find what is AR, aspect ratio. So AR is equal to, can be written as CL square divided by pi E CD0. So this is the formula we are going to use for this finding the value of AR. Then this is the direct substitution. So all the values are available in the problem. Then we can substitute, then we can find the answer. That is AR is equal to 10.18. So this is the aspect ratio value. So in this video, the last problem is an airplane is in steady level flight with a true airspeed of 50 meters per second. Then ambient air density and the ambient air pressure at a flight altitude is given as 0.91 kg per meter cube and 710 power 4 Newton respectively. At a sea level, the air density is 1.225 kg per meter cube and the ambient pressure is 1.01 into 10 power 5 Newton per meter square. This is 10 power 5. Here Newton per meter square. They can write it here. So here there should be a meter square and it should be 10 power 5. So the equivalent airspeed or indicated airspeed we have to find in terms of meter per second. We know the basic relation with respect to indicated airspeed and the true airspeed, whereas the true airspeed is equal to equivalent airspeed into the density ratio, that is the root of rho naught divided by rho. So the true airspeed, equivalent airspeed, the rho is actual density, the rho naught is sea level air density, that is the standard atmosphere, that value is 1.225 kg per meter cube. So from this given formula we can find what is equivalent airspeed. So the equivalent airspeed is equal to, the formula can be written as TAS into the inverse of this, that is rho divided by rho naught. So the TAS value is given in the problem, that is 50 meter per second. Then rho, that is the density value at the altitude, that value is 0.91. The rho naught value is 1.225. Then power 1 by 2. So the equivalent airspeed or the indicated airspeed value is 43.09 meter per second. So this is the simple formula we can apply here to find the equivalent airspeed or indicated airspeed. So the answer is 43.09 meter per second. Thank you so much.